So, hi everyone, and welcome to this third lecture in series on stellar winds. So today we have the pleasure of having Kostas Antoniadis doing a PhD in Athens, who will speak about opticalistic winds and the stability. But before that, let me introduce him a little bit more. So he's doing his PhD in final year of PhD, and then before he did his master's studies in Amsterdam, and he is currently at ESA for a 3 months research visitor program. The topic of his PhD thesis is the loss of red supergiant, and as far as I know, it told me has a paper that is going through review at ANA on investigating the metallicity dependence of the mass loss rate for red supergiants. So stay tuned for his paper. And yeah, I think it's all about our speaker. So, Kostas, are you ready?
Yeah, sure.
So,
Thank
please, the floor is yours.
yeah, thank you. So I'm glad to present this interesting topic to you today. We're going to start with, let me show you first the outline of this lecture. We're going to start with a brief introduction on the winds of hot stars and some of the uh, basic theoretical models for the winds that were already discussed in the previous lectures. And then we are going to focus on the optically thick winds and the bistability jump and the luminous blue variables. So starting with this introduction, we know that photons interact with the metal ions and that momentum and energy are transferred by line scattering. And what this means is you can see in this nicely in this figure that when a photon interacts with an ion, it gets absorbed, moving the electron to a higher energy level, and then it can be re-emitted again. And when this re-emission happens in a different angle, this leads to a momentum transfer. So the most dominant ions for the line-driven winds are carbon, oxygen, nitrogen, and iron. And also we can see the different radiation processes that occur between photons and ions in this figure. What we already discussed is the line transitions, absorption and re-emissions, moving the electron to different energy levels. And then we can have other interactions that we are going to also discuss in this talk is the recombination of an electron to an ion, and also when we are going to refer to continuum-driven winds, we should know that we have the bound-free, free-free interactions, plus also the Thomson scattering between electrons, that all of them can contribute to the opacity. Now, about the line transitions that we're going to see, we can have multiple line transitions with above of 100,000 to millions of lines, and specifically, as we're going to see later, for optically thick winds, that iron contributes, as you can see on the right, mainly in these processes. And now we can go briefly so some of the theoretical models used. The Castor, Abbott, and Klein theory that was discussed in more detail in the previous lecture, and you can go to that too. So I will briefly mention some things that here in this theory, they express the radiative acceleration in terms of force multiplier m, which is multiplied with the Thomson acceleration. And then this m can be expressed with a Sobolev velocity gradient. And if we take the equation of motion at the supersonic part of the wind, we can have two terms of the gravity and the radiation pressure, where the radiation pressure can be approximated using this Sobolev velocity gradient. We're going to discuss about the equation of motion later in more detail. Now, this theory assumes steady and spherically symmetric isothermal flow, and it neglects multiple scattering which occur in the wind. So we need to simulate the radiative transfer through a complex and expanding atmosphere. And here comes the Monte Carlo method, which was also discussed in the previous lecture. So in this method, the photon packets, let's say the photons are tracked from the photosphere to the outer wind, as you can see in this scheme here. And in its interaction, as we mentioned, we have absorption and re-emission, and this, its time, transfer momentum and energy. And now if we calculate this energy in its interaction and we take the energy conservation equation, we can estimate the mass loss rate. And this was done by Fink et al., deriving this mass loss recipe shown here with respect to luminosity, the stellar mass, the effective temperature, and the terminal velocity. Now, the main drawback of the CAK and the Monte Carlo method is the Sobolev approximation, which fails below the sonic point and around it. However, I should mention that since most of the mass loss occurs at the supersonic point, the Monte Carlo method is still a good approximation. And the other method, the comoving frame method that was also discussed in more detail in lecture 1 and also in lecture 2, is the direct integration of the radiative acceleration in the comoving frame, and it's applicable for both optically thin and thick winds. Okay. Now let's see, when we're referring to different kinds of winds, let's say, where the different types of stars are located in the HR diagram. So when we mention usually the optically thin winds, we refer to the O-type stars during the main sequence, and then the thick winds will be at the Wolf-Rayet phase located here. And finally, we're going to talk about the luminous blue variables too, which are at the upper right part of the HR diagram near the HD limit, and where these type of stars can transit the HRD in very short time scales. And here in this Kimpenham diagram, we can also see the structure of such stars and evolution. This is an example of a 60 solar mass star. You can see the different regions with burning regions and where we have convective regions. And starting in the main sequence as an O-type star, at some point we can go through the LBV phase where a significant amount of mass can be stripped from the star in a very short time scale, as you can see. And then we reach to the Wolf-Rayet phase, depending on which phase we are, as an N-type or C-type, and depending which element is more abundant. Okay, now we can move on to the optically thick winds and discuss more details about them. We start with a calculation of the radiative acceleration, which is the integral of the opacity multiplied with a flux. And now this, in the diffusion approximation, it can be estimated by this equation where we have the Rusland mean opacity and the luminosity. Now, the Rusland mean opacity, in general, the opacity, if we define it, we can say it's the average transparency of the gas. And the Rusland mean opacity specifically is commonly used for stellar interiors, because it is valid in the diffusion approximation, and it's weighted over the mean free path of the photons. As you can see, it's defined by this equation where here it's the Planck function. And however, the outer part of the wind, line driving is what dominates the opacity. So we should use here the flux weighted mean opacity. And you can see on the plot on the right that the two definitions, so with the red line it's the flux weighted and the blue dust is the Rusland, that the two opacities agree at the inner part. And then when we go above the sonic radius, they start to deviate significantly. Yeah, when also line driving is what dominates the opacity. So now let's see what initiates the optically thick wind. For this, we need also to define the Eddington ratio, which is the ratio of the radiative acceleration over the gravitational one. And it's also proportional to the opacity, the luminosity, and over the stellar mass. And now this ratio is crossed at the sonic point, so right of these dust vertical lines you see here. And it means it goes above 1. So this means that the radiative acceleration overcomes gravity, and the optically thick wind can be initiated. And as you can see here, there are two opacity peaks that contribute to this. Yeah, and now we can see which ions contribute mainly to these opacities. Now on the y-axis you have the ratio of the radiative acceleration over the gravitational one, and the dust red line shows the overall contribution of all the ions. And we see here at the first peak that it's the iron ions, as you can see with gray, dominate the wind, and then we can have even more ions at the outer part of the wind. So we have two bumps, and I should mention that there is also another peak at 1 million Kelvin in the stellar interior, but it's not relevant to the wind. And these bumps are usually referred as the hot iron bump and the cool iron bump, or the iron bump and the helium bump, because you can see that helium also contributes significantly. Okay. Now, having defined better the optically thick winds, we can now derive the transition mass loss rate between optically thin to thick winds, or in other words, from very massive O-type stars, let's say around 100 solar mass star, to Wolf-Rayet stars. We're going to use some equations here, but I think it will be easy to follow going step by step. First of all, I should mention that we assume a hydrostatic equilibrium below the sonic point, and here we have the equation of motion, where we have a term from the gravity, one term from the gas pressure, and one term from the radiation pressure. And the right-hand side of this equation is equals to 0 below the sonic point. So now what we're going to derive is at the supersonic region. At the supersonic region, the gas pressure is negligible, so we can neglect it. And then if we multiply this equation with 4 pi r squared, we can rewrite it in this form. Now, on the left-hand side, this term is the mass loss rate coming from the mass continuity equation. And we can also rewrite the equation with respect in terms of gamma with the definition we saw earlier. And then if we use also the definition of the optical depth for the region above the sonic point, we can rewrite it this way, replacing dr with d tau. Okay. So now we have this equation, and if we assume that gamma is much larger than 1 at the supersonic region, then this term can be approximated to 1. And now we can easily integrate this equation, and we reach this part where we have the Maxwell's rate, the terminal velocity, luminosity, and the optical depth. And now, if we define that the point where we have the transition from optically thin to thick winds where tau is equals to 1, we can derive the transition Maxwell's rate. And now the significance for this definition of the transition Maxwell's rate is actually it's a luminosity determination of the transition from optically thin to thick winds or O-type stars to Wolf-Rayet stars. Because as in absolute values, the Maxwell's rate can have many uncertainties, but the significance of it is the luminosity determination. And I should mention that the only assumption that we made up to this point is the hydrostatic equilibrium below the sonic point, and that radiation pressure dominates the wind. So this derivation is we come to this result regardless of any other assumptions of wind clamping, etc. But this derivation was not exact, since we assumed that gamma was much larger than 1. And if we do this calculation again of fully integrating numerically this part, we reach to this result having one extra term of this factor f. And this factor is around 0.6. And its uncertainty on this factor is even lower than the uncertainties we can have in luminosities or even in terminal speeds. Okay, now having derived theoretically this transition Maxwell's rate, we can compare with empirical results. So now you can see some empirically derived Maxwell's rate on this plot versus gamma. And you can see the different types of stars, the O-type stars here, and then Wolf-Rayet stars here. And we observe a kink or a transition at one point between these two. So in the end, these empirical results confirm what theory predicts. Now we can also discuss if there is a metallicity dependence for the Wolf-Rayet winds. In the past, it was thought that since carbon is more abundant than iron, then we shouldn't have any metallicity dependence. But as I mentioned earlier, and if you remember that plot, iron involves millions of spectral lines. So involves many more line transitions, which contribute also to the opacity. And as you can see on the plot on the right, we see a strong metallicity dependence with the Maxwell's rate. And at very low metallicities, you can see that this curve is flattening, and this is because now carbon lines dominate. All right, now we can move to the final part of this lecture about the bistability and the luminous blue variables. But what is the bistability jump? As the star evolves, we know that it cools down, And this means that at some point it can reach a temperature where iron 4 recombines to iron 3. This happens at around 2000 Kelvin. And this in turn means that we have more line transitions that can absorb the photons, which increase the opacity. And this in turn, as we know, will enhance the radiation pressure. So this is depicted on the plot on the right, starting at hot temperature with fast winds, and then after a point when this recombination occurs, we see a jump to by around an order of magnitude to higher mass loss rates, to slower but stronger winds. And then you can see another jump here, which occurs when iron 3 recombines to iron 2, but we're not going to focus more to that. You can see that also we have lack of data for even lower temperatures. And now, is this jump related to the luminous blue variable phase? On the left, I have we have an image of from HST of AG Carina, which is also named as an S-Doradus variable. And these type of stars experience heavy mass loss, and it is possible that the bistability jump is the effect of it results in such mass loss. And these type of stars can transit the upper HRD in timescales of years, very fast. So you can see here an HRD with S-Doradus variables, and the location of the bistability jump around 20,000 Kelvin. But we also have some cases of LBVs that there are observed giant eruptions in the order of 10 solar masses, like Eta Carina, as we know. But what is the driving mechanism behind it? Because all the things we have mentioned till now cannot explain all such a giant eruption. So for this, we are going to start again with the equation of motion. You know already all these terms. And if we use the equation of state for the pressure, where A is the sound speed, we can rewrite it in this form. And now these two terms are negligible again compared to the radiative acceleration in the gravitational one. So we can rewrite it in this form, where we have a term of the sound speed over the velocity. And we can also again rewrite in terms of gamma. So now we know that at the sonic point, v will be equal to the sound speed. And this in turn means that gamma at the sonic point equals to 1. So above the sonic point, we are going to talk for gamma above 1, and we're talking about super-Eddington winds with increased opacity. And now, because if we are in a regime with a very high opacity, the medium can have instabilities and be also inhomogeneous, or as it is referred, it is porous. Now, porosity is significant because this way radiation can leak through different channels and escape, let's say, the star or the wind. This, let's say, limits up the radiation pressure, because otherwise, imagine if you had a very optically thick, homogeneous medium, and with very high radiation pressure, this would completely disrupt or destroy the star. So porosity helps to keep it somehow stable. And if the entire atmosphere then is super-Eddington, meaning that the sonic point is located in the envelope of the star, then continued driving becomes possible, meaning we have all the interactions I mentioned in the introduction about Thomson scattering, bound free and free interactions, which all of them contribute to the opacity, and we can have very high mass loss rates. And this could explain in the LBV giant eruptions I mentioned before. So going to see some takeaway points here. We discussed about optically thick winds and when they initiate at the opacity peaks, so we saw involving millions of iron lines. The transition mass loss rate is a luminosity determination from optically thin to thick winds or O-type stars to Wolf-Rayet. And then the bistability jump. It's a temperature dependent change when iron 4 recombines to iron 3, and we have increased opacity and high radiation pressure, and this could explain the mass loss we observe in S-Doradus variables. And finally, what I mentioned about super-Eddington continuum-driven winds that can explain the giant LBV eruptions. And that's it. Thank you.
Thank you very much for this overview. It was really interesting. Do we have questions? Well, we had a question in the chat, but I see that it's answered. No question? Then I will take the chair opportunity to ask a question. So here you talk about the bistability, and that is possible explain for S-Doradus variables, but are there other observations of other type of stars that explain this bistability jump? I mean, observationally.
Yeah, I'm not sure if I know the answer to this question.
Okay.
Someone else maybe from...
Yes, Alex?
Yes, Evkaristo Kostas, very nice presentation. Yeah, my question is about the implications in the, let's say, real universe of that mass loss transition and luminosity transition in particular. So what that does mean that beyond such luminosity, you don't, there are no stars having optically thin winds, O-type stars, and below you don't have thick, or not exactly?
So you mean yeah, below the luminosity of the transition if
Yes.
if we have Wolf-Rayet stars or not?
Okay, so you are or are not expected to find Wolf-Rayet WNH below that a luminosity value.
Yeah.
That should be universal.
Yeah, I think so, actually. Jörg maybe answer better. I mean, my expertise in is on red supergiants, so yeah, these were new to me.
Okay, thank you.
Yeah, I could just briefly mention it as Kostas asked for it. Yes, of course, these stars here, they are all main sequence type stars. So these are the main sequence O stars and the main sequence Wolf-Rayet stars. So they more or less have the same temperature. And so you can sort of read log gamma here as a sort of L, right? But of course, in another temperature regime, like in the classical Wolf-Rayet stars, that doesn't necessarily have to be the case, of course. You can have luminosities much lower that are still optically thick.
Oh, no, I mean, I can understand that.
But the gamma will be high, even for the classical Wolf-Rayet stars, they will have a high gamma.
No, but my question is like, because I mean, it's a distinction in luminosity. So it's like, in terms of observation, it's like we have O-type stars only beyond such limit, and all of the stars that we find at larger luminosities are only WNH, or not the case?
If you look at the original paper about the transition mass rate from 2012, you can see a table of luminosity determination. See that all the O stars have lower luminosities than all the W and H stars. They have higher luminosities. And it's the luminosities in between the O stars and the W and H stars that are OF/WN. So these are transition type stars. So indeed, in that case, when you have a nice sequence in one cluster, then you will have exactly that that sequence, yeah.
Okay.
Yeah, so as usual, I have also maybe two comments. At first, thanks a lot for the nice overview of the talk. I think one needs to mention two things, namely one with respect to your question, Sophie, and another one with respect to the talk. So your question was on the bistability jump, not for the S-Doradus stars, but in general. And I mean, from what Kostas has shown us, these are theoretical predictions, and it seems that they should depend only more or less, really, on the temperature of the star, because this argument that you obtain more and more lines from iron 3 cannot be, how to say, cannot be neglected. So, but when you look into the observations now, I guess that Yorick will not completely agree with me because this is a long-standing debate. Anyhow, I think what he will agree also is that at least the observations tells us that the jump which you would or let's say the other way around, that if at all, you would observe only a very weak jump, not on the order of 1 decade, which was mentioned by Kostas. There are, of course, certain stars where you see some increase of the mass loss rate, not types of stars, sorry. Certain types of stars where you might see an increase in the mass loss rate going to lower temperatures, but not on the order of a decade. And so this is something which is still completely unclear, because the theory makes more or less clear, at least when you do the simple theory, that there should be some jump. However, of course, there are also newer calculations which are done by these comoving frame calculation, which was also mentioned by Kostas and which was discussed in the very first talk of this series. And they seem to predict that the jump is if at all, quite weak, simply because its velocity stratification in the sonic region is somewhat different. So, but this is still an open question. So my personal view would be that you do not see a strong jump, if at all, and one shall be careful when one is using these kinds of jumps in the evolutionary tracks. So that was my comment number one, and comment number two is very brief, namely, you were speaking about the optically the continuum-driven winds, and you were mentioning porosity, which is one of the possibilities. By the way, there are nowadays also other possibilities which are related to the increase in enthalpy in the wind, but that's something quite complicated and quite new, so I don't want to bother you with this. But the important point here is the following, namely the porosity. This mechanism which you have shown here is only working when the porosity is changing as a function of distance from the star. Namely, when you have in the photosphere and the subsonic region quite a strong porosity, and in the supersonic regime more or less no porosity. When you would have a constant porosity, then this would not work, because then you would not change the Eddington factor. So you need to change something with the Eddington factor, and this is typically explained by changing the porosity. So these were my two comments. Thanks a lot.
Thanks a lot, Joe. Yorick, I don't know if you want to comment. I saw you were.
No, I completely
Oh.
agree with everything Joe was saying.
Good.
Okay. Good.
No.
Do we have any other questions for Kostas? I don't see any. Well, then I propose that we thank the speaker again, and then we meet in 2 weeks' time for the next talk. Thank you.
Thank you.